In this video, we'll discuss non-steady state diffusion. You may wonder, what does non-steady state mean? Non-steady state means the process is time dependent. In the case of diffusion, if diffusion is non-steady state, we'll have two variables. The first variable is time, and the second variable is distance. Mathematically, diffusion can be expressed by the partial differential equation. So dc, c is concentration here, over dt is equal to dx, then capital D, that's diffusion coefficient, dc over dx. If we condense everything on the right, we can get capital D, then d squared c over dx squared. This type of partial differential equation has a special name. It is called parabolic partial differential equation because it resembles the equation y equals to ax squared. This type of partial differential equations are very powerful. Not only they can describe diffusion in material science, it can also describe heat transfer in material systems. Since non-steady state diffusion is time dependent, therefore at different times we'll have different concentration profiles. On the x-axis, that's distance. On the y-axis, that's concentration. Let's mark C0, that's the initial concentration of some chemical species in the material. Let's also mark Cs, that's the concentration of the chemical species on the surface or at the diffusion interface. At different times, you get different concentration profiles. Here are three examples. In this case, T3 is greater than T2, greater than T1. In all three cases, all the concentrations start from Cs, and all of them approach eventually to C0 as you go deeper and deeper into the material. Also, as T increases, you have more and more chemical species present in the material. In diffusion studies, we usually want to know the concentration at position X in the material with given temperature and the time. Then how can we do the calculations? The solution for the above partial differential equation is as follows. Cx, that's concentration at position X, minus C0, that's the initial concentration, over Cs, that's the surface concentration or the concentration at the interface, minus C0, equals to 1 minus error function x over 2 square root dt. The capital D here is the diffusion coefficient, t is time. You may wonder, where is the error function from? The error function is from the Laplace transform. For those who have studied ordinary differential equations, you know that Laplace transform is a very powerful tool to solve differential equations. I will not go through the details here. Next, I'll do a very quick comparison of steady-state diffusion and non-steady-state diffusion. For steady-state diffusion, it is time independent. That means the concentration profile will not change over time. In reality, for most of the steady-state diffusion, usually it's a thin plate. At each side of the plate, you have a constant concentration. In this example here, C1 is greater than C2, and the concentration profile is a straight line. For non-steady state diffusion, it is time dependent. As you have seen not too long ago, the concentration profile changes over time. For non-steady state diffusion to occur, you need a very thick block. The block is so thick that it only has an entrance and no exit. And if we draw the concentration profile as a function of distance, it's no longer a straight line, it's a curve. Let's look at an example that elucidates the non-steady state diffusion. We will be looking at carbon diffusion in a low carbon steel. C0, that's the initial carbon amount, in the steel is 0.25 weight%, then Cs is 1.2 weight%. We also know that Cx at position x is 0.8 weight%. X is 0.5 millimeters under the surface. The diffusion coefficient is 1.6 times 10 to the power of minus 11 meters squared per second. The question is, how long does it take to do diffusion to achieve a concentration profile described above? We will use the equation from the previous page. On the left-hand side, that's Cx minus C naught over Cs minus C naught, and plug in the numbers. On the right-hand side, that's 1 minus the error function x over 2 square root dt. X, turn that into meters, that's 5 times 10 to the power of minus 4 meters. Diffusion coefficient d is known, and t, the diffusion time, is something we're looking for. On the left-hand side, we have 0.421 equals to the error function. Then we need to look up at the error function table. The value 0.4210 is between 0.3794 and 0.4284. In this case, we know the value z, the value within the error function bracket, is some value between 0.35 and 0.4. If we do a linear interpolation, we get z equals to 0.392. Then plugging all the numbers, we can get the diffusion time is 25,400 seconds, or 7.1 hours. So in order to achieve this concentration profile, you need 7 hours in this condition. If you think about it, you need to do 7 hours diffusion. This is quite long. In order to speed up the process, what can you do? I'll give you 3 seconds to think about it. A more efficient way is actually to increase d, the diffusion coefficient. Then how to increase d? You can increase temperature. At a higher temperature, you can achieve similar results within less time. This is the last video on diffusion. In the next few videos, we'll touch upon the solidification in metals and alloy systems.